Hi everyone, this is Dr. GVR Seshagiri, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So in this module, I want to explain design of a connecting rod numerical problem. In previous session, already we have learned the design procedure. So according to that procedure, how to solve the given problem. So how to solve the given problem on connecting rod, I will explain now. The construction details of connecting rod already have discussed in the previous session. So once again we will see. So here the connecting rod has small end bearing and big end bearing and shank. The major the important components are small end and big end and shank. The shank is a high section. So here see the problem on connecting rod design. A connecting rod is required to be designed for a high-speed 4-stroke IC engine. The following data are available. So diameter of the piston is 106 mm. The mass of reciprocating parts is 22 newtons. And the length of connecting rod, that is center to center, so 340 mm. And stroke is 140 mm and RPM is 1600, 7 developing 50 kilowatts, and the possible over speed is 2400 RPM. The compression ratio is 7:1. The probable maximum explosion pressure is here 2.5 Newton per mm square. So that is at about 3 degrees. So here the given problem on connecting rod is for 4-stroke IC engine. So the available data is design of a diameter of the piston and reciprocating parts 22, mass is 22 newtons. So according to our design procedure, we have to solve this problem. So how to solve this problem I will explain. In first step in our design procedure, so what are the dimensions of cross section? Here the step 1 is cross section is I section. So first find out the I section dimensions. So this is the I section. This is flange and this is second flange and this one is web. So what are the dimensions here? The T is small t, thickness of the web, and this is capital H, the depth of the I section, and width of the section is here capital B, that is 40. So the web thickness is you can represent with small t. The depth of the web is 3t, so you can represent with small h. So that here B is, the depth is 40 and capital H is 5t, and small h is 3t, and you can assume the small b, that is width of the web. Width of the web b is, you can represent with b, that is t. So find out Ixx and Iyy. So here Ixx, moment of inertia about x-axis, is 1 by 12 into bh cube minus small bh cube. So already you know what is h and what is capital H. Capital H and small h, and capital B and small b, already you know as shown in figure. So substitute those values here in place of b, that is 40, capital H is 5t, and small b is t, and h, small h, 3t. So find here, you will get one value in terms of t. Similarly Iyy. So here Iyy value according to the cross section of I section, 2t b cube plus h t cube. So substitute the capital B value in this, 1 by 12, 2t, and capital B is 40, and small h, that is 3t, multiply with t cube. So we will get the Iyy value in terms of t. After that, find out area of the cross section. So that is 2 multiply with 40 into t plus 3t multiply with t. So here 8t square plus 3t square, 11t square. So this is the area of cross section. So why I have taken here 2 times of 40 into t. So once again see the cross section here. So this is flange and second flange. So the flange having the thickness is t, and this is width is 40. So the area of the rectangle is length multiply with breadth. Here 40 multiply with t. So that's why multiply 2 times multiplied, plus 3t into t. So this is 3t, and this is small t. So finally you will get 11t square. So after that, find out kxx and kyy. Kxx is equal to square root of Ixx by a, and square root of Iy by a. So this value also you will get in terms of t, small t. So here you will get Ixx is equal to 4 Iyy. 4 Iy. So after that, so calculate the buckling load. Buckling load is equal to sigma c to multiply with the area of cross section divided by 1 plus into L by K whole square, that is slenderness ratio. Sigma c is compressive stress, and area cross-sectional area, and small a is Rankine constant. So the Rankine constant have to take from design data book according to given material. So the L is the length of connecting rod, and K is radius of gyration. So similarly, buckling load about this is x-axis, and the similarly buckling load about y-axis, y-axis. So that is sigma c the a plus L by KYY. So already all these things we have discussed in design procedure. Now calculate force on a connecting rod. So that is gas force. So that is area multiplied with gas pressure 5/4 multiplied with d square to maximum gas pressure. So that is a gas explosion inside the cylinder. So that is that pressure you should take here. So multiply with d, that is the piston diameter or cylinder bore. You will get a gas force. This gas load equal to the buckling load. So now buckling load equate to the gas load. So buckling load you will get in terms of small t. This value obtained from this relation. So equate this value to buckling load, you will get find t value. So for this problem, so the t you may get 3 mm or 4 mm. So that is this value depends upon your assumed value, assumed material. So suppose if you obtained calculated value is 3.5, you may take 4. So thickness of the flange or web is calculated. So now calculate the other dimensions of cross section. So what are the other dimensions? B, H and small h. The capital B is 4 multiplied with T, and capital H is 5T, and small h is 3T. So this is the width of the cross section and the depth of the cross section, and this is the depth of the web. So now the dimensions are calculated. After that, the step 2. Step 2, as we discussed in design procedure, dimensions of crank pin at crankshaft, and what are the dimensions of small end bearing. So that is by using those values we will calculate by using this relation. So that is load at crank pin multiply with the area multiply with the bearing pressure. So what is the area of crank pin? So that is L, length of the crank pin multiply with the bearing pressure. So we will get the L length and DC. But here two unknowns are there. So that's why here assume L by DC. L by DC is equal to 1.5 to 2. So you may take from a design data handbook. No need to remember this value. The tabular form is available in a data book. Similarly, calculate the small end bearing dimensions. So here also same, the small end bearing pin, here load at a piston pin. So that is again the small end bearing length, and D multiply with bearing pressure. So here also you have to assume L by D ratio. L by D ratio you have to take from design data book. Next step is the bearing cap bolts dimensions. So how to calculate the bolt dimensions I will explain here. So generally 2 or 4 bolts are used for connecting rod. For design of bolts, the core diameter is important. So next step, find DC. So that is the core diameter of a bolt. So you use this relation for calculating the core diameter. This is inertia force 5/4 into DC square multiply with the maximum pressure. So how to calculate this inertia force? The one formula is available in a data book. Here also I am giving here. So mr omega square. So multiply with the cos theta plus cos 2 theta by n. So here theta is the angle at the top dead center, and n you may calculate by using L by R. So calculate inertia force and equate to this 5/4 into DC square into phi maximum, that is the load on the bolt. Find DC. After finding the DC, you may fix bolt dimensions. Next, finally, the thickness of cap. The thickness of cap by using bending moment. So the bending moment you may calculate by using sigma into Z. So that is a bending moment of section. Sigma B value at bending load bending stress you may take from design data book, and Z is the section modulus. So by using this relation, find width of thickness of bearing cap. So here so Z equate to BC square by 6. So B is here width of the bearing, and C is the thickness of cap. So you may take B is equal to length of the bearing. So already we have calculated in a previous step the length of the bearing. So the bearing length is almost equal to width of the bearing. So you substitute this value in this equation, and Z already calculated, and find here C. So that is thickness of bearing. So here have completed all steps. In dimensions of cross section is completed, and dimensions of big end bearing and small end bearing, and bolt dimensions, and finally thickness of cap. So this is the design calculations of a connecting rod problem. So for this solving for this problem, I have taken the references, UC Jindal, and data book is K. Mahadevan. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.